In this video, I'm going to show you how to find the volume of a revolution for a parametrically defined curve. A parametrically defined curve means that the x and y variables are now functions of a third parameter which we'll call t. So you can see here that x is equal to 3t squared and y is equal to 3t minus t squared, where t is greater than or equal to 0. In a previous video, I covered how to find the volume of a solid revolved around the x-axis. We found that the volume is equal to pi times the integral between the limits of a to b of y squared with respect to x. For parametric equations, we can adjust this formula so the volume now becomes pi times the integral of y squared, and because x is now a function of t, we can say this is dx over dt. And then when we multiply this by dt, we can see that this division of dt, and we can think of this as a multiplication, these two will cancel. But because we're now integrating with respect to t, we need our limits to be in terms of t. So we'll say our first limit is when t equals a, and our second limit is when t equals b. So this is the formula that we use when we find the volume of a revolution for parametric equations. Okay? So if we look at this example, we've been told that this region, this shaded region, is revolved around the x-axis. So there's a couple of things that we need to do. The first thing we need to do is we need to find our limits in terms of t, because this 12 and 0 are given in terms of x. So when x equals 0, when it's 0, we can use this parametric equation for x, and this will be equal to 3t squared. So t will also be equal to 0. And if we look at the next x value, when x equals 12, well, 12 is now equal to 3t squared. We'll divide both sides by 3. So 4 is equal to t squared. Then we'll take the square root, so t must equal 2. It can't be the negative 2 because we're told that t must be greater than or equal to 0. So these are our limits. We've got t equals 0 and t equals 2. So now we need to work out dx by dt. And we're told here that x is equal to 3t squared. So if we differentiate this, this will be equal to 6t. So now we can say the volume is equal to pi times the integral between the limits of 0 and 2 of y squared, and we're told that this is equal to y, so we'll say 3t minus t squared all squared multiplied by dx by dt, so multiplied by 6t integrated with respect to t, so dt. So we can tidy this up by moving the 6 in front of our integral and expanding out in these brackets. So now we get the volume is equal to 6 pi times the integral between 0 to 2. And when we expand in these brackets, we get 3t multiplied by itself, so 9t squared. We get 2 lots of 3t times negative t squared. So this becomes negative 6t cubed. And then we get the negative t squared multiplied by itself, so positive t to the 4. And this is all multiplied by t and integrated with respect to dt. So now we'll expand out with t, and we get the volume will be 6 pi times the integral between the limits of 9t cubed minus 6t to the 4 plus t to the 5. So now we've simplified this, we can evaluate this integral, and we get the volume is equal to 6 pi. We'll add 1 to this 3 to get 4, then divide by the new power, so 9 over 4 t to the 4, minus 6 over 5 t to the 5, plus 1/6 of t to the 6. Between the limits of 0 to 2. So now we'll substitute in each of these limits. So the volume will be 6 pi. T to the 4 is 16. So this will become 9 over 4 lots of 16. T to the 5 is 32. So minus 6/5 of 32. And then T to the 6 is 64. So plus 1/6 of 64. And when we substitute in the 0, well, 0 to the 4, 0 to the 5, and 0 to the 6 all become 0. So this is take away 0. So a volume will be 6 pi. 9/4 of 16 becomes 36. This becomes 38.4. And this becomes 10 2/3, which I'll round to 10.67. So a volume will be 6 pi times 8.27 approximately, which is approximately 49.6 pi, or 156 units cubed. Okay, so I hope that's given you an idea about how to find the volume of revolution for parametrically defined curves. You can download the full lesson and worksheet from my website, mrmathematics.com. There's a link in the description below. Thanks again and take care.